In this lesson, we will take a look at conic sections, specifically the first conic section that we are hopefully the most familiar with. So before we do that, the general overview for what a conic section is, as the name implies, conic, coming from cone, it's a piece of a cone. So if we take a cone and we slice it with a plane, we're going to get these various conic sections. So the first one that we've got here is what we're going to be looking at today, and it's this sort of brown piece there that's highlighted, and that looks most like, hopefully, a parabola. So that's the first conic section. That's where we take the plane and we slice it at an angle, going through one side out of the bottom. Over here, this is not a perfect picture, but the cone is being sliced perpendicular to the base by the plane, and that resulting section there is a circle. So we've definitely dealt with parabolas in algebra. We know all sorts of information from their formulas. Circles we've probably seen in geometry, maybe not as much in terms of an equation to generate a circle, but we've definitely worked with those before. The next two we've definitely worked less with. This next one is similar to a circle, but it's cut on an angle, so that produces an ellipse. And then the last one here, we actually take the two cones. The reason why we've had two cones the whole time is for this last one. We have these two cones stacked and we cut it vertically this time, and we end up with these two little pieces that almost look like parabolas, but they are not. This is called a hyperbola. So that is our hyperbola. This is going to be the most unique of the set. It's probably the one that people have seen the least. It doesn't really show up in geometry or previous algebra courses, and that's more advanced than what we're used to. But today we're going to start easy. We're going to look at the parabola, which again, we are hopefully familiar with from our time in algebra. There are a few things, though, that we're going to add on that you probably haven't seen before in terms of a parabola. So this, first of all, it's opening sideways. Usually our parabolas are opening up and down. So we are going to talk about that. The direction of the parabola is determined by the setup of the equation. For this one, though, it really doesn't matter which way it's opening. There's just these 5 key features that we want to look at here. So the first, the most important, is the axis of symmetry, and that is a formula that we've had in algebra. That is part of the quadratic equation. It is the opposite of b over 2a, and that tells us where the middle of this lies. The other term that we might be familiar with is the vertex. The vertex is the point on the parabola that goes through the axis of symmetry. It's generally the min or max if we have a parabola that opens up and down. It is the x-coordinate for that y-coordinate we find from the axis of symmetry. The next two pieces, the directrix, and the focus, are probably terms that we've not heard associated with a parabola. We've probably heard of a focus before, and that is kind of the same thing if you've heard about it in science. The focus is where the, if you would, the light beams would refract and they would all be pointed to that focus. So no matter where you shine a light, they would all be pointed to that same place. That is the reason why we use lenses to focus light. Anyway, the directrix then is this line, this dotted line on the other side of the parabola. And the focus and the directrix are related to each other with that last little piece of information there, P. So the focus is always the same distance away from the curve of the parabola as is the distance from the parabola to the directrix. Those are always the same length, and that's demonstrated on this picture with the two tick marks there showing congruence. That's the geometry. So P is the distance from the focus to the vertex, and then the focus and directrix are always the same length from each other. So if we go from the vertex to the focus, that would be a distance of P, and then even though it doesn't quite look like it in my picture, if we go from the vertex to the directrix back here, it should be that same distance P. So really what we'll be doing when we are solving these, we'll go through the formulas which are down here on the bottom of the screen, and then we're going to plot this picture. And the most important things we need to plot are the vertex and then the focus, and then the directrix. Once we have those three things, we just draw in the parabola, and we're good to go. Okay, so here are the formulas for the parabolas, and the direction matters, and it comes from the letter that's being squared. So that's the first piece of information that I've got right here on both of them. If the x quantity is squared, so that is the way we are used to seeing it, y equals x squared, our standard parabola. If the x quantity is squared, then it's opening up or down. If the y quantity is squared, then it is opening left or right. And if you look at these two equations, they are strikingly similar, and that is going to be true throughout all of conics. The different orientations of the shapes of the conics are going to have the same formula with the letters just rearranged, and it'll also be very, very similar formulas for the other three. Circles, ellipses, and hyperbolas, excuse me, also share a very similar formula. Not quite so much with these parabolas. These are a little bit more unique, but there are commonalities between all of the equations. So for the vertex in all of these, vertex or center, we're going to be using h and k. So the h is always the x coordinate, so it's in all of the parentheses with the x. No matter where the x is, it always has an h with it. And then the y is going to have the coordinate k, the letter k, with it. So y minus k, you'll see that in both of those. Those are the coordinates for the vertex, h and k. The focus, again, depends on the direction that the parabola is opening. So if it's an up and down, then it is affecting the y, since it's up and down. So you'll see k plus p there. If the parabola is opening left and right, then we are affecting the x-coordinate going left and right, so it's h plus p. The axis of symmetry is just whatever h or k for the correct letter. So if it's an x squared parabola, then the axis of symmetry is the x equals h coordinate, and for the y squared, it's y equals k. And then the directrix is going to be the opposite letter of the axis of symmetry. So if the axis of symmetry is x, the directrix is y, and it's y equals k minus p. So these formulas are a little bit intricate, but once you have h, k, and p, then everything works out very, very easily. You just plug in all of these numbers and you find your coordinates and you're good to go with graphing. So we've got this first example here. It's written in this, what I call vertex form, and that's the easiest form that they can give us. If they give us a different form, which we'll see a little bit later, then we're going to have to do some algebra to rearrange it into this kind of formula, but this is the best formula to start. So this is more akin to like a standard form of the equation that tells us the most information. So the first thing to do is to realize which direction our parabola is opening. So if we have the x squared, it's opening up or down. If it's y squared, it's opening left or right. And then how do we know if it's up or down? How do we know if it's left or right? We know that from the p-value. So if the p-value is positive, it opens up or to the right. Those are generally associated with positive movement. And if it's a negative p-value, then it's opening down or to the left, which are, again, normally associated with negative movement. So that is the determination for which of the four directions does this thing open. So at first look here, we should see that the squared term has a y in it. We got y squared. So that means our parabola is either opening left or right. So we're going to be working with that set of information, that part of the formula. So this is either left or right. And how do we know if it's left or right? We look to this number out front of the x parenthesis. So it's negative 12. That means our p-value is negative. So we have a negative p-value, which means our parabola is going to open in a negative direction, so left. We've narrowed it down, it is opening to the left. So whenever we do all this graphing, our parabola should eventually look like that. Okay, so now we need to start taking pieces of information off of this equation. So we're just going to go from left to right and work with what we have. So the first is y minus k quantity squared. So we have y plus 5 quantity squared. There's different ways to think about it. Whatever way makes the most sense to you. The k value is basically the easiest way to think about it. It's not necessarily the most correct way to think about it, but the k value is whatever numbers with the y but the opposite sign. So this is y plus 5, which means k is going to be negative 5. Easiest way to think about it. I'm not going to go into any other crazy details on it. Just think about it's the opposite of whatever's with the letter. Okay, onto the other side, we have this negative 12. If we look at our equation, and that's why that 4p is underlined, 4p is the number out front. So we have negative 12. So what we need to do with this number every time we're working with a parabola is we need to take this number out front and divide it by 4, because really what we have is negative 12 is equal to 4p. That's what this part of the equation is telling us. So we have negative 12 equals 4p. That's pretty easy. P is negative 3. And then finally, inside the x-coordinate with is h. So h is equal to the opposite of that. So it's x minus 2. The opposite is 2. So now we have the three most important values that we need to go onto the graph. So we have k, h, and p. We're ready to go onto a graph. So the first thing we should do is, once we make our xy coordinate plane, plot the vertex. So that's the most important point. That's kind of the center of everything, and the h is the x coordinate and k is the y coordinate. So it's vertex, you can write that out, it's helpful, is 2, negative 5. I would really suggest writing out all of the information as we have it right here. So these 4 pieces, write that out every time so you know what you're doing, you know what you're graphing, and that way it's easy to see what you've done. So we go to 2, and then negative 5, and that is our vertex. Okay, so we have the vertex. The next thing to do is the focus. So the focus is h plus p and k. So k is not changed, negative 5. H, which is 2, plus p, which is negative 3. 2 plus negative 3 is going to be negative 1. So we said this thing is opening to the left. And if we just rudimentarily, I can't say that word right now, just draw in that parabola, we have the focus being, and this is not math terminology at all, eaten by the parabola. So that's the best way to think about it is the focus should always be inside the parabola should always be eating the focus. That way you know you've got it plotted on the correct side of the vertex. The next thing to do is the axis of symmetry. And the axis of symmetry is just the y-coordinate, so y equals negative 5. So that is going to be this line that connects the focus and the vertex. Go ahead and extend that axis down. And then our last thing would be the directrix D. So the directrix is h minus p. So that is the opposite of kind of how we found the focus. So we're really going to the other side. So we have 2 minus negative 3. 2 minus negative 3, that gives us 5. So 1, 2, 3, 4, and 5. And this is going to be a line, dotted line. So the focus, again, and the directrix are equidistant from the parabola. So if you go 3 to the left to get the focus, you go 3 to the right to get the directrix. That's a little bit easier, I think, than necessarily doing the math. Not that it was hard math to do 2 minus 3. But anyway, we should be kind of symmetric with all that stuff, and that's a good check to make sure you can just count your spaces and make sure it's the same distance on both sides. The parabola that I drew in might not be the exact shape, and I'm not too concerned with the exact shape of this parabola. I'm more concerned with the pieces of information that we've got right here, these 4 pieces of information. The general shape I know is correct. It's opening to the left, the vertex is in the right place, the focus is in the right place, the directrix is in the correct place. We've got all of that correct. The parabola might be a little bit wider, a little bit narrower than we've got, and I'm okay with it not being exact. If you really want to get exact with it, you can always pick a x and y coordinate, or pick a coordinate and plug it in and see what you get for the other one. Anyway, I'm not going to go through all that, but you can pick x equals 2. That would give you. So if we pick, yeah, like x equals 0, we'd have to do a lot more math with that, and I'm not worrying about doing that. But if you really want to get exact answers, you can always pick values and plug them in and see what you get. So this is good enough for me. So we will move on to the next example. So in example 2, this is more like what we would see in an algebra setting. This parabola, we can absolutely graph this. If you got a graphing calculator, you can graph this very easily. No matter what kind of graphing calculator, it should be able to handle this. And that's great. This is the actual standard form of the parabola, the quadratic really, because we can use this to solve. We can solve quadratic formula for this, a, b, and c. Those are the coefficients. That's old stuff. We're not going to go through all that today. We're not solving these. We're just graphing them. But this form isn't conducive to what we need to do. And what we need to do is graph this. And the equation needs to be rewritten in this vertex form with the x minus h quantity squared, so on and so forth. So what we need to do with this is we need to solve this, not solve this, but we need to rearrange this to be in that factored form. And this is going to require a lot of factoring knowledge from Algebra 2. So this is something that it's a little bit more challenging. It's not just, pick out the numbers, do a little bit of division and addition. There's going to be some substantial work for this one. So the way we're going to start this off, and this probably isn't something that we would do normally, we're going to take that 6 and just kind of move it off to the side for a second and work with these two terms since they both have x in them. We really need to get these x pieces factored in to be a perfect squared quantity. So we're going to leave this 6 off to the side and come back to it a little bit later. So the first thing we want to do is we want to factor out whatever leading coefficient is on the x squared. Now this is a very specific set of steps and it needs to happen this way pretty much every single time you're working with something like this. Doesn't matter if it's x or y, but it needs to happen in this very similar way every single time. So what we're going to do is we're going to take 1/4 and put it in front and have a plain x squared. So we need that x squared to have a leading coefficient of 1. When we factor out negative 1/4 from this 3x, what we're really doing is 3 divided by negative 1/4. Fractions, I know, keep flip change, keep change opposite, however you want to think about it. So we're really doing 3 times negative 4 over 1, so that should be minus 12x. So that step needs to happen correctly. If you don't do that factoring correctly, then the rest of the problem is going to be very screwed up. Okay, so we have this. Now, we are still not at something that we can factor into like a difference of 2 squares or a perfect square trinomial or anything like that because we only have 2 terms. So what we need to do from here is we need to complete the square. I'm not a fan of completing the square. I don't do it anywhere else in mathematics other than for these conics, and I don't find any joy in it. It's what we have to do here though. So we have to complete the square. So what we're going to do is we're going to take this middle term and divide it by 2, and then we're going to square that. So negative 12 divided by 2, it's always going to come out positive when we square it, so it doesn't really matter the sign. But negative 12 divided by 2 is negative 6, and when we square that, we get 36. So what we're going to do, again, we take that b term, we divide it by 2 and square it. So we're going to add 36, and then right away we're going to subtract 36. And this is why I don't like completing the square, because we're adding 36 and subtracting 36. We're not doing anything, but we're doing a lot of things. It's really weird. Anyway, we have this now. What needs to happen is this positive 36, or whatever positive number you have, needs to stay inside, and then this negative needs to go outside of the parentheses. So here's another kind of challenging part. When we take that negative number out of the parentheses, it has to be multiplied by whatever coefficient is hanging out front here. So we need to take this negative 36 and multiply it by negative 1/4. And when we do that, negative 36 times negative 1/4, we're going to end up with a positive 9. So that positive 9 goes on the outside. This is gone from the inside, so what's left is this. and we still have that negative 1/4 out front. So we are still technically balanced. We haven't changed the value of this expression, but we have done a lot of rearranging and a lot of putting in new parts to compensate. So we have this, which is a perfect trinomial squared. So this is what we're building towards. This is why we want to do completing the squared, to get this perfect trinomial. This will always factor. It should always factor. If you did it correctly, it will always factor to x minus whatever that middle term divided by 2 was. So this should factor to x minus 6 quantity squared, x minus 6, x minus 6. If you did completing the square correctly. And that's, again, the reason why we do completing the squared is to get this perfect square trinomial. So we have that up front, and then we have a 15 hanging out on the end. So really this whole time it should have been equal to y, and I've just been lazy, but now we're going to bring that y back in. So to complete this problem, what we need to do is we just need to get that squared term by itself. So right now there is a multiple on the front of it, and there is addition on the end of it. So we need to get rid of both of those things to get the squared term by itself. If you look at both of these formulas, the squared term is by itself. The p value is on the non-squared term. So what we want to do first is get the 15 over, so this will be y minus 15 equals, go ahead and throw that in parentheses, negative 1/4 x minus 6 quantity squared, and then the last step is to get that 1/4 over. So to get that 1/4 over, we are just going to multiply by negative 4. So we have negative 4 y minus 15 equals x minus 6 quantity squared. So that is all of the front work to get this into the vertex form. So we did a ton of algebra, and we are just now ready to do what we did in the first problem. So this is a lot more work when we have it in this standard form. We have to do completing the squared to get it into this form to know what the focus and vertex are. Is this efficient? Absolutely not. Again, we could have graphed from this equation, but what if we had this same equation in terms of y? It's going to be a lot more challenging to graph that, especially if you've got an older calculator that doesn't allow you to put like y squared in. So doing all this work will make it easier to graph, especially by hand. Okay, so the first thing we want to do is get h, k, and p. So h is the quantity with x opposite sign, so with x minus 6, that means h is positive 6. K is the number with y, but the opposite sign, so 15. And p is the coefficient over here divided by 4. Don't forget to divide by 4. So negative 4 divided by 4, p is equal to negative 1. From there, we can do everything else that we need. Vertex is hk, so it is 6, 15. What's next? Focus. So the focus is going to be h and then k plus p. So 6 and then 15 plus negative 1 is 14. The axis of symmetry is going to be x equals 6. And then the directrix is k minus p. So k is 15 minus p minus negative 1, that gives us 16. So there's everything we need really quickly to do this. I'm not going to get exact with it, but 6 and 15 is there. 6 and 14 is here. And the directrix is at 16, so we'll call that here. Axis of symmetry is here. So this one should be open downwards, and we can actually get that from the very original equation. Since it's an x squared and it's a negative leading coefficient, that is a downward opening parabola. Again, something we should have covered somewhere in algebra. So this should make sense when we fill this parabola in. It is eating the focus, and there we go, something like that. Again, that's very approximate, but it gives us all of those important features that we were looking for. Okay, we have one last example here, and the example here doesn't even give us an equation. They give us the 2 points. They give us the focus and the vertex. That's all they give us. And the Oh, we have two more examples, excuse me. So there is not a lot to go on here, seemingly, but we actually have everything we need right from these 2 points. So what I would suggest doing is very quickly graphing these to see their orientation. So the vertex is at 1, -4, again, not exact, but it's going to get us in the ballpark. And then the focus is at 3, -4, so 2, 3, -4. Okay, so going back to that statement I made in the first problem, the vertex, not the vertex, the parabola always eats the focus. So if this is the vertex and this is the focus, the parabola always eats the focus, which means our parabola is opening that way. So it's opening to the right. Opening to the right tells us exactly which version of the formula we're going to use. So the version that we're going to use is what I've already got here for you. The y squared, and the p is positive. So that is the version of the equation that we're going to use, and we get that just from these two little points. Okay, so the next thing that we can actually determine is p, and p is just the distance from the vertex to the focus. So from 1 to 3, the p-value should be 2. And we are ready to write an equation. So this is actually probably the easiest set of information that they can give us. So what we're going to do is we're just going to use this version of the equation. Don't know why it was so small there. Let me make that a little bit bigger. And fill in everything that we have now. So it's going to be y minus k. So k is the y coordinate of the vertex, so -4. So it's really just y minus -4. Quantity squared equals 4. The p-value we said is the distance between the focus and vertex, so the p-value is 2. And then x minus h, and h is the x-coordinate there, so x minus 1. Definitely want to clean that up a little bit. Y plus 4. 4 times 2 is 8. X minus 1. That's it. Again, that's probably the simplest version of this we could ask for, the quickest to find, and there's really no algebra involved, just a tiny bit of arithmetic and basically plugging in a couple of pieces. Okay, so this one is definitely the last one. This is actually very similar to the example 3 that we just looked at. They're giving us the vertex again, and then this time they're giving us the directrix. So that's dirx, that's all short for directrix. That's not the x coordinate or anything like that. So they are giving us more or less the same information, slightly less because we don't know exactly from plotting these two things which direction this opens, but we will be able to determine that in about 2 seconds once we do have it graphed. Okay, so the vertex is at -2, +4. So that's approximate, but that's the vertex. And then the directrix is at the line y equals 1. So that is a horizontal line, y equals 1. Okay, so we actually should be able to then determine which direction this opens. So take 2 seconds, think about it in your head. This is going to open up. It's going to open up. The directrix is below the vertex, which means the focus has to be on the other side. So what we want to do is determine how far the vertex is away from the directrix. So from 4 down to 1, that distance is 3. So to graph the focus, we would go the other way, 3, and our focus would be there. So if we go up 3, that's going to be -2, +7. So it really is one tiny extra step more work than the previous example. We have the directrix. We can very easily find the focus given that directrix. We just determine how far away it is from the vertex and go that far in the other direction. So here we have it. If we do a very rudimentary parabola, it's there and it is opening up. So that means the x is going to be squared, and that means that the p-value is going to be positive. So we'll go back up here. We are using this one, so let's see if I can get that. Bring that down just so we have it to work with. Boom, there we go. Okay, so the vertex we know is 2, 4, the directrix is 1, the focus is -2, 7, which means our p-value, our distance is 3. That's everything we need to plug into the formula. So we would have x minus the x coordinate from the vertex, -2, quantity squared, equals 4 times the p-value, which is 3, and then y minus the y value here, which is 4, and there we go. So again, like the previous problem, we just want to clean it up, get rid of that double negative, do the distribution with the p, so we have x plus 2 and 12 y minus 4. And boom, there we go. So the last two examples we had here, super quick, super straightforward. Obviously, if they give us the um, equation already in vertex form, it's pretty easy there. I know we didn't write out the axis of symmetry and all that for these, but you can follow the pattern and do that from the equations that have given you, the formulas that have given you, and go through and do that. The only one that's challenging, in my opinion, is the factoring one. And it is challenging to get that set up, get that work done, and if you've not done completing the square, it's not a super hard process. Again, I know I talked it down a little bit, but the process is pretty orderly. There's steps to follow, and if you go through and follow those steps exactly, you're going to be in good shape. It's just a lot of steps, and there's a lot of maneuvering of the numbers, and there's a lot of room for mistakes. So be very, very careful with those. That'll probably be the one that gives you the most trouble. Everything else should be pretty straightforward if you have any of the other three forms. So that's it for parabolas, and next time we'll take a look at circles.